Welcome to the Chapter 2, Section 2 podcast. It's on the properties of water. And water is a molecule and it is neutral, meaning it has the same number of electrons and protons, as we said before, but it's polar. And we'll get to what polar means in a minute. The oxygen atom has 8 protons in its nucleus, and therefore it attracts electrons. And when it bonds covalently with the hydrogen atom for that pair of electrons, the electrons are more likely to be found near the oxygen atom because those 8 protons inside are pulling the electrons closer to the oxygen atom than they are to this hydrogen atom. So that you're going to find those electrons nearer to the oxygen atom than you are going to the hydrogen atom, and therefore that is going to create a charge in the molecule. If you look at the molecule, and we'll see in the picture in a moment, you're going to see that the oxygen end of the water molecule has a slight negative charge because the electrons are found closer to it, and the hydrogen end has a slight positive charge because the electrons are not found near there, so there's more positive particles on that side of the molecule. Let me just go back 1 second to this one, and you can see right here we draw a negative sign here, we draw positive signs here to show that these parts are positive by the hydrogen end of the molecule, and at the oxygen end of the molecule it's negative. And they often call this molecule the Mickey Mouse molecule because of the shape of the molecule. The hydrogens are at one end of the molecule and the oxygens at the other end. So let's keep going forward. There it is. Here's your water molecule, and because you have partial and negative charges, they will attract each other. The one water molecule will want to stick to another water molecule, and the positive end of one water molecule, like for instance this hydrogen here, which is positive, will want to stick to the oxygen end, which is negative. So these two water molecules, 1, 2, will want to stick together to each other. So the attraction between them is what's called a hydrogen bond. That's when the positively charged hydrogen atom wants to stick to the negatively charged oxygen atom. The hydrogen bond, you'll hear us say this over and over again. And they're not very strong bonds. They're not nearly as strong as covalent or ionic bonds, which is an important point. Here's another look at it. Here's the negative end of the oxygen atom, and here's the positive part of the hydrogen atom, and they're going to stick together right there. So as a result, they can have as many as four different hydrogen bonds with one molecule. So if you look at this molecule in the middle that's labeled, the atoms are labeled, it can stick to 1, 2, 3, 4 other water molecules as a result. So this gives it special properties. So there we go. Hydrogen bonds formed between water molecules. First property is called cohesion, and it's the attraction between molecules of the same substance. In this case, between two water molecules. And you can see the water here is beating up on this car. The water molecules are sticking together to each other, and they're forming these beads. If you take some water and put it on the tip of your finger, you'll see that the water likes to clump together on your finger. So water is extremely cohesive because of this hydrogen bond. And so you also see drops of water forming on surfaces. Here you go. Here's the on a spider web, and here it is also the water on the water. On like a pond, the water will stick together on the surface of the pond, which allows very lightweight insects such as and spiders to walk on that surface. Now, adhesion is the attraction between molecules of different substances. And in this case, water is going to stick to the glass molecules of this graduated cylinder, and you can see there's a slight dip in the water level on this and gives us what's called the meniscus of the in the beaker. The property of adhesion also allows water to do some pretty clever things, like basically defy gravity. In this case, we have water being pulled by what's called capillary action through up this paper towel right here. It's basically climbing the paper towel because it's adhering to the paper towel itself and climbing up it. You also can do that. Capillary action is what forces water up out of the roots of plant and up into the stems and leaves. And you can see I chose this. I guess it's a rose of some type. And what they've done is they've put a dye in the water that's fed to the rose, and the dye then ends up inside the white rose and tints the white rose this purplish color. Solutions and suspensions. So we're going to talk solutions and suspensions are mixtures, and it's when a mixture is a material composed of two more elements or compounds, and they're physically mixed but not chemically combined, meaning the atoms are not bonded to each other. So there are two types that mixtures that you can make with water. The first one being a solution, second being a suspension. The solution, for solution, the components are evenly distributed throughout the solution. With the salt water is an example where the salt is evenly distributed throughout the water. In this case, table salt is the solute, the substance that is being dissolved, whereas the solvent, the substance that is doing the dissolving, is water. Here's a picture of it, and what happens is the polar molecules, remember sodium chloride, salt, has negative chlorine ion and a positive sodium ion, and when mixed in water, the ions are attracted to the opposite sides of the water molecule. So here it is not quite dissolved. We've just put the salt in the water beaker, or maybe we've just added the water to the salt in the beaker, and you can see that the salt molecules are starting to separate from each other and cling to the water molecules. This is a chlorine atom right here, and here you can see a sodium atom. Here's a better one, a sodium atom clinging to the opposite sides of the water molecule. So, and what this is showing is, the ions, the sodium ions and the chlorine ions are breaking away, and as they disperse, you form a solution. So in actuality, the sodium and the chlorine are actually not actually bonded to each other anymore. They're actually, through a hydrogen bond, loosely bonded to the water molecules. So, and water is able to dissolve a lot of ionic, remember those are things with charge, ionic compounds, and molecules that also exhibit polarity, just like they do, have a positive side to the molecule and a negative side. And one of those molecules is sugar. Sugar has a positive and a negative side, and here we see somebody dissolving dissolving sugar in water. So water is the greatest solvent on earth. A suspension, in a suspension, the materials don't dissolve, but they don't settle out. They kind of separate into the water, but they don't actually they don't actually dissolve, meaning the molecule separates. The picture I chose here is of a very muddy river, and which the mud or the dirt is what's being suspended in the water. And what keeps the molecule suspended is the movement of the water. So you kind of have to shake it up to keep it moving. And when you don't have dissolved material, we call this obviously a suspension. There are some biological fluids that are both solutions and suspended. And the blood has a lot of dissolved compounds in it, so that would make it a solution. But it also contains cells and other dissolved particles that remain in suspension. So blood, in some ways, is dissolving some compounds, but it also has other cells and particles suspended in the blood. Now we're going to talk about acidic and basic solutions. So in order to understand acids and bases, we need to look at a water molecule again. And so water molecule is neutral because it is really made of two ions, a hydrogen ion and what we call a hydroxide ion. And remember, it's H2O, so here's one hydrogen atom here, which is positively charged, and then on the other part of the molecule could be thought of as the hydroxide ion, which is negative, which consists of the oxygen atom and the hydrogen atom. So if we put that into an equation form, H2O is equal to a hydrogen ion, a positively charged hydrogen ion bonded to a negatively charged hydroxide ion. So scientists use a scale, it's a measurement system called the pH scale, to indicate how many hydrogen ions are in a solution. And the scale ranges from 0 down here up to 14 here. At 7, right here, the hydrogen ions and the hydroxide ions are equal, and that's what pure water is that has a pH of 7. It's just hydrogen ion and hydroxide ions together. So solutions below 7 are called acidic because they have more hydrogen ions than hydroxide ions. And some common things that are acidic are acid rain, tomato juice, lemon juice. We've all drank lemon juice. And something really nasty is stomach acids, which you find in your belly to help you digest. So the lower the pH number, the greater the acidity. This is important to remember. Now solutions with a pH above 7 are called basic because they have more hydroxide ions than hydrogen atoms. So the higher the pH, the more basic the solution. You can see some of them are soap, ammonia solution, bleach, oven cleaner. These you can see a theme running through this. These are all things that you clean with. So an acid is any compound that forms hydrogen ions in a solution. And this is just reiterating what we said, that pH values below 7 have more hydrogen ions and they are acidic. So strong acids, really strong acids, ones that can really do harm, are between the range of 1 and 3. And hydrochloric acid, which is what is in your stomach, is a very, very strong acid and helps you digest food. A base is a compound that has hydroxide ions in a solution, and we sometimes call them alkaline also. So you have to remember that word, basic and alkaline. And they have, once again, this is a review, they have lower concentrations of hydrogen oxides, and they have pH values above 7. One strong base is called lye, and these are both products with lye, and you can see they're both drain openers. And they have pH values very high, up in between 11 and 14. And unfortunately this is so small, but what I wanted to show you on this slide was that the pH values of fluids within most cells of the human body have to be between 6.5 and 7.5. Basically they have to be neutral. And I already circled this before when I was preparing this show. You can see what falls right in this area right here are things like urine, which is a solution found in the human body, saliva found in the human body, egg yolks, and cow's milk, which are both fluids found in living organisms. So you can see they're all roughly the same. And even things not that far off, coffee, safe drinking water, those are things that are very close to being neutral on the pH scale. So, and if you have things that are higher or lower in pH, it's going to affect the chemical reactions that occur in your body. So therefore you need to control pH. This is part of homeostasis, maintaining a steady internal environment. One of the ways you can do it is through what's called a buffer. And buffers are weak acids or bases that can react with the strong acids or bases that are already in your body to prevent sudden changes in pH. You can see here I've added, in this case, we've adding hydrochloric acid into a weak base, which is then causing the hydrogen ion, the hydrogen atom to no longer bond with the chlorine atom, and which is then basically making it a changing the pH of the hydrochloric acid to a higher number. So here's the quiz.